Before I start, anyone has any questions? Any questions on the homework or anything else that we did in the class? I did send you the link for the integral test video. In case you forgot something that I said in the class, you might want to look at that. Any questions at all? No? Okay, if you don't have any homework questions, I am going to start section 11.4. 11.4 will not be on the third exam. 11.4 will be on the final. Once again, please write down the homework: 3, 5, 7, 17, 21, 29, and 31. Section 11.4 is on what we call the comparison tests, and there are two of them, so we're going to learn two new tests to determine whether a given series is convergent or divergent. Remember, in section 11.2 we learned whether if you have a geometric series, then whether the geometric series is convergent or divergent depends on the common ratio, right? In 11.3 we learned the integral test, right? And that is also a test to determine whether a given series is convergent or divergent. We are going to learn two more today. Let's start with an example. Let's ask the following question. The series number 1, the sum of 1 over 2 to the n plus 1, n going from 1 to infinity, is this series convergent, right? Is this series convergent? Well, first of all, whenever you are given a series, it would be nice to have some intuition or a good guess whether or not you think it's convergent or divergent. Now, if you make a wrong guess, that's fine. You'll realize pretty soon you made a wrong guess. But if you look at the series that I have here, the denominator, if you sort of ignore the 1, right? Ignore the 1, what type of series do I have? If you ignore the 1, what's that? P series is n in the base, right? P series is 1 over n to the p. Right? Here n is in the exponent. If you ignore the 1, what type of series do you have? Geometric, right? Because common ratio would be half, right? Everybody is okay? So if I look at the series 1 over 2 to the n plus 1 and ignore the 1, it looks like a geometric series with common ratio being half, right? Everybody realizes that. Okay. Then we know that the geometric series will be convergent, right? Because the common ratio is between -1 and +1, right? So when the common ratio is between -1 and 1, we know that the geometric series is convergent. So we would guess that this series is convergent as well, right? Wouldn't you guess? If without the 1, if it is convergent, then you would assume that with the 1 it should be convergent as well. So how do we decide whether or not this is convergent or divergent? Well, we can compare the partial sums of this guy with the partial sums of the geometric series here. So I'm going to call this the second series. This is the first one. And we are going to compare their partial sums. So let's say Sn is the nth partial sum of the first series, and Tn the nth partial sum for the geometric series 1 over 2 to the n. Okay, is that clear? And let's compare these partial sums. You guys agree that 1 over 2 to the n plus 1 is smaller than 1 over 2 to the n? Why does that inequality hold? 1 over 2 to the n plus 1 is less than 1 over 2 to the n. Why does it hold? They have the same numerators, but the denominator on the left is bigger, right? So if you divide 1 by a bigger number, don't you get a smaller ratio? Is everybody okay with that? So 1 over 2 to the n plus 1 is smaller than this because the denominator here is bigger than the denominator here, while the numerators are the same. In other words, if you take the reciprocals, right? If you take the reciprocals, do you get a true inequality? If you take the reciprocals, right, you're going to get 2 to the n plus 1 is bigger than 2 to the n, which is correct, right? Am I making sense? 2 to the n plus 1 is greater than 2 to the n. So if you take the reciprocal, then 1 over that is less than 1 over 2 to the n. Everybody agrees with the inequality, okay? So what does it tell you? It tells you that every term of the first series is smaller than the corresponding term of the second geometric series, right? Every term. So remember, we have two series here. The first one and the second one being the geometric series, right? So what we are saying here is that every term of the first series is smaller than the corresponding term of the second series, right? So that implies that the nth partial sum of the first series, right? The nth partial sum of the first series is smaller than the nth partial sum of the second series, right? Because each term in Sn is smaller than the corresponding term in Tn, right? You guys realize that? Everybody is okay with that. So Sn, the nth partial sum of the first series, is smaller than the nth partial sum of the second series. Remember, nth partial sum means you're adding the first n terms. Now, Tn is the nth partial sum of which series? Tn is the nth partial sum of this series, right? Now, this is a series of positive terms. So the nth partial sum of the series is smaller than the sum of the series, right? What is Tn? Tn is equal to this guy, but n going 1 up to what? Well, I have a little bit bad notation here. I'm using an n here, and then I'm using n again here. I should be using a k here, okay? Just to make them different. So what I'm saying is that Tn is the sum of the first n terms of this guy, right? So Tn would be smaller than the sum of the entire series. Okay? But the sum of the entire series is a finite number. We know it's a geometric series, it converges and so on. So that tells you what? That tells you that the nth partial sum of series number 1 is always smaller than 1, right? So on the other hand, the series number 1 we have, that's a series of positive terms, right? It's a series of positive terms. So Sn is an increasing sequence as n is increasing, right? Because as you increase n, it means that you're adding more and more terms with Sn. So Sn is an increasing sequence, but it is bounded. Sn is bounded. So Sn is bounded, it is increasing. And we know that whenever you have an increasing sequence bounded above, it's got to be convergent, right? So we know that the limit of Sn exists, right? The limit of Sn exists, it's a number. So Sn is a convergent sequence. Therefore, the series is convergent, right? Did that make sense? So that's for this example. So generally, how do we use this concept? Suppose that I have two series, sum of AN and sum of BN, two series, and these are both series with positive terms. They both have positive terms. Number one says, suppose that sum of Bn is a convergent series. Sum of Bn is a convergent series. Let's assume that. Then, if you have that An is less than Bn for all n, then the series An is also convergent. Is that making sense? So basically what it is saying is that assume that I have two series and the second series is convergent, and we are saying if every term in the first series is less than the corresponding term of the convergent series, then this series got to be convergent as well. Right? The second one is saying that suppose that the series of Bn is divergent. Suppose the series, the sum of Bn is divergent. That would mean that the nth partial sum for this sum is going to infinity, because this is a series of positive terms. So if this series is divergent, it means that the limit of the nth partial sum is infinity. So if this is divergent, and if we know that every term in the first series is bigger than the corresponding term in Bn, in the divergent series, then we know that the first series must be divergent as well. Is this making sense? Are these two statements making sense? So suppose that I have a series An, okay, and I want to know whether the series An is convergent or divergent. And let's say that I can find a series Bn, and I know that the series Bn is a convergent series. And then I can show that every term of the series An is less than the corresponding term in the convergent series. Well, then the series must be convergent. So if you have a series and every term of the series is smaller than the corresponding term of a convergent series, then that series is convergent. That's what we are saying. The second one is saying, if you have a series An and every term of the series is bigger than the corresponding term of a divergent series of positive terms, then the series must be divergent. Does that make sense? If every term of your series is bigger than, let me say the first one again. If every term of your series, let's say you're given a series, you want to show whether the series is convergent or divergent. How would you do it using this? Well, if every term of your series is smaller than the corresponding term of a convergent series, then your series is convergent. If every term of your series is bigger than the corresponding term of a divergent series of positive terms, then your series is divergent as well. Okay. Now, on the other hand, if you have, suppose you have a convergent series. So suppose that I show that every term of your series is bigger than the corresponding term of a convergent series. What can I say? I can't say anything. If I have a series and I show that every term of my series is bigger than the corresponding term of a convergent series, then I cannot say anything. Okay? Is that making sense? Let's look at usually whenever you are using the comparison test, right? What you need to do is that you're given a series, then you have to come up with your own. You have to come up with a known series that you know whether that series converges or diverges, and you need to compare that with your series and see if it is convergent. Usually, these are the two types of series that you use. Okay, for the series Bn, you use either a p-series or a geometric series. Okay. And do we know when a p-series converges? A p-series converges exactly when p is what? Greater than 1. And a p-series diverges when p is less than or equal to 1. Geometric series converges when the common ratio is between -1 and 1. And the geometric series diverges when the common ratio is larger or equal to 1 or less than or equal to -1. Okay? Okay, let's look at another example. Let's say I have this series. This is a very similar, these are the kinds of problems you have in your exercise, okay? Let's say the question is determine whether the series converges or diverges. Okay, the series is the sum n going from 1 to infinity, 5 divided by 2n squared plus 4n plus 3. Does this series converge or diverge? That's the question. So how would I use my comparison test to do this? Anyone? What would be what should I do? First of all, I have to find another series to compare this series with. Okay, I need another series which I know converges or diverges, and I need to. Well, first of all, I need to. It would be nice to come up with a guess. Do I guess that it is convergent or divergent? What did you guess? Was it? How many of you say convergent? How many say divergent? How many say don't care? Okay. All right. So it's convergent. Why would you guess that? In the denominator, the highest order term is this guy. So if you ignore the other terms, what you have is 5/2 n squared, right? Take the 5/2 outside. Maybe I should write that down. So what I'm saying is that in this example that I have, the sum n going from 1 to infinity, 5 over 2n squared. What's the second term? Plus 4n. So what I'm saying is that if you ignore the second two terms, the last two terms in the denominator, then each term looks like what? 5 over 2n squared, right? So you have the sum n going from 1 to infinity of that, and that is equal to 5/2 sum n going from 1 to infinity of 1 over n squared, right? What type of series is that? Is that what's that? P series with p bigger than 1. So it is a convergent series, right? So this is convergent. So that gives me the guess or intuition that my series that I have, that should be convergent as well. So that's just a intuition. So how do I now show that the series is indeed convergent? Everybody's clear? So my guess is that this series should be convergent. So if I want to use the comparison test, what should I do? I need to find a series which is a convergent series, and I have to show that every term of my series is smaller than the corresponding term of the convergent series. Am I making sense? You have to find a convergent series, and you have to show every term of this series is less than the corresponding term of the convergent series. Okay? Now, what convergent series would you use? You're going to use that 5 over 2n squared because you know that it's convergent. You're going to compare your series, this series, with the known series, right? So let's do that. First of all, is this inequality correct? The term, the nth term of my series, is it smaller than 5 over 2n squared? Was that? Why is that? Obviously, the denominator on the left is bigger, right? So you're dividing the same number 5 with a bigger denominator, right? So obviously, the ratio on the left has got to be smaller than the ratio on the right. Is that making sense? You guys okay with that? It's like saying 2 over 5 is smaller than 2 over 3, right? 2 over 5 is smaller than 2 over 3. Everybody is clear with that? Okay. So because this inequality holds, what we have then is that every term of the given series is smaller than the corresponding term of a convergent series, because we know that the series 5 over 2n squared, that series is a p series with p being 2, so it's a convergent series. So now we could say, by using the comparison test, we know that the given series is convergent. Is that making sense? So first of all, what did we do? We were given a series. We want to test whether the series is convergent or divergent. And what was our strategy? Well, first of all, we guessed whether the series is convergent or divergent. And our guess was that the series was convergent. And then we are saying, well, if I want to show this is convergent, then what I have to do is I have to show that every term of the series is smaller than the corresponding term of a convergent series. And then we have a guess for what convergent series to pick, right? And then we did this. Now, one thing you want to make sure, though, that the series that you have is a series of positive terms. If you want to apply the comparison test, your term, the terms of the series should be positive. Is that making sense? Now, in my test, when I wrote down the test here, I said they are series with positive terms. It doesn't have to be that every term is positive. What you need is that all the terms are positive after some point on. Maybe after the 10th term, all the terms are positive. If the first few beginning terms are negative, that's okay. Am I making sense? So you can relax this condition a little bit. Okay, as long as all the terms are positive except for first few finitely many, you're okay. You can still apply this. Is that okay? Same thing goes for these inequalities. They don't have to be satisfied for all n, as long as they are satisfied for all n except for the first few. That's okay. Okay, so any questions on this example? Any question? All right, now let's look at a different test, which is the following. We said all this. Let's look at this series here. What's the difference here? Well, before I had 1 over 2 to the n plus 1. Now I have 1 over 2 to the n minus 1, right? And again, I want to test whether the series is convergent or divergent. Again, my guess would be what? If I ignore the negative 1, I have the geometric series, and my guess would be it's convergent. However, the inequality, remember we had an inequality that says 2 to the n plus 1. 1 over 2 to the n plus 1 is less than 1 over 2 to the n, right? That inequality doesn't hold if I change this to a negative 1, right? In fact, this is the other way now, right? Is that making sense? So now I have every term of my, if I try to use this inequality, then every term of the given series is bigger than the corresponding term of a convergent series. Well, that doesn't tell me anything. Am I making sense? If I could show that every term is bigger than the corresponding term of a divergent series, then I could say that my series is divergent, right? But we are guessing that our series is convergent in this case. So what should we do? Well, in this case, it's easy to use another test instead of using the comparison test that we just used. What's this other test? The other test is this called the limit comparison test. So you have the comparison test, and then you have the limit comparison test. So what is this test? Suppose that I have two series, sum an and sum of bn, and both of these series are they have positive terms. Okay. And suppose that if I take the limit as n goes to infinity of an divided by bn, then I get a number c, let's say, and let's assume that c is a number bigger than 0, strictly bigger than 0. So the limit of the ratio of corresponding terms, the limit of the ratio of corresponding terms of the two series is the constant c, which is greater than 0. That's what we are assuming. If that's the case, then either both series converge or both series diverge. Am I making sense? If you have two series of positive terms, and if you have that this limit is a number greater than 0, then either both of them converge or both of them diverge. Am I making sense? So in order to determine whether this series is convergent or divergent, here's what are we going to do. Our guess is that it's convergent, so we are going to use a convergent series and take the ratio of the corresponding terms and take the limit. Well, in this case, we are obviously going to use the same geometric series. We know it's convergent. Let's take the ratio of this guy and this guy. Let's take the ratio and take the limit and see if you get something bigger than 0. So I'm going to take an to be 1 over 2 to the n minus 1, bn to be 1 over 2 to the n. Take the ratio of the two. If you take the ratio of the two and take the limit, what would you get? What would be your guess for the limit? Well, if you take the ratio 1 over 2 to the n minus 1 divided by 1 over 2 to the n, right? And then you simplify that, you're going to get 2 to the n divided by 2 to the n minus 1, right? Do you guys agree with that? Because when you have 1 over 2 to the n minus 1, and then you have to multiply with the reciprocal of this, right? So 2 to the n divided by 2 to the n minus 1. What is the limit of this guy? What is the limit? What's the limit? You have 2 to the n divided by 2 to the n minus 1, right? And what's the limit of that? In the denominator, you can factor out 2 to the n and write 1 over 2 to the n like this. And this is 2 to the n. Are we okay with that? 2 to the n, 2 to the n cancels out. What's the limit? What's the limit of this guy? 0. So what are you left with? 1. So the limit is 1. And since the limit is 1 and it's greater than 0, we can say that we compared our series with the series 1 over 2 to the n, right? So by the limit comparison test, either both series converge or both of them diverge. Since one of them converge, the other one should be converging as well. So now we could say that by using the limit comparison test, the series that we have in hand is convergent because the other one is a convergent geometric series. Did that make sense? Did that make sense to you? Okay, I am going to do another example, which is this example. let's say the question is, this is a very similar question to some of your homework problems that I assigned. Again, the question is, determine whether the series is convergent or divergent. Okay. So what should I do? Well, let me do it by hand. 2n squared plus 3n. Okay. So the example that we have in hand here, is that I have the series n going from 1 to infinity. What do I have again? 2n squared 2n squared plus 3n, is it? Divided by, I have a root, and what's that? 5 plus n to the 5. So that's the series that I have. First of all, what did you guess? Is this convergent or divergent? What's your guess? What is your guess? Is it a convergent series or a divergent series? Numerator, denominator, they have powers of n, right? So when n is big, we can ignore the lower order terms. Ignore the lower order terms. What are you left with? Write down. What are you left with if you ignore the lower order terms? Just keep the highest order terms. What do you get? No, not quite. Okay, so if you ignore the lower order terms, in the numerator, what do you get? 2n squared. In the denominator, you have root of n to the 5, right? Okay, so that's what? What's the root of n to the 5? N to the 5 half, right? Okay, what is that equal to? Isn't that this to the what? 1 half. Right? Everybody is okay with that. So I am going to compare this. So my intuition is that this is comparable to the series sum n going from 1 to infinity of 1 over n to the half. And what kind of series is that? What kind of series is that? Geometric P series? It's a P series, and it's a divergent P series, right? Because P is less than 1, it's half. So my guess would be that the series that I have in hand is a divergent series, right? Everybody is okay? So how do I show that it's a divergent series though? This is my guess only, okay? That's my intuition tells me that this should be divergent. But how do I use my theorems to show that it is a divergent series? Well, first of all, let me apply the limit comparison test. Now, in order to apply the limit comparison test, what do I have to do? Because I want to show that my series is divergent, it means that I have to use a divergent series, take the ratio of the corresponding terms, take the limit, and show that the limit is a positive number. Okay, if I take the ratio of the corresponding terms of the given series and the divergent series, I have to guess what divergent series I want to use. Well, my guess is clear. I'm going to use the P series as the divergent series. I'm going to take the ratio of the ratio of the corresponding terms and take the limit. So let's take the ratio of the corresponding terms. So here's I have 2n squared plus what was it again? 3n divided by 5 plus n to the 5 root of that. I'm going to call that an, okay? Call that an. And I'm going to call bn to be 1 over n to the half. And I'm going to take the ratio of an and bn. And if I take the ratio of an and bn, what do I have? I have 2n squared plus 3n divided by 5 plus n to the 5 square root divided by 1 over n to the half. And so what is that? 2n squared plus 3n divided by 5 plus n to the 5 multiplied with n to the half, right? Are we okay with that? So what do I get? Well, now I have to take the limit. If I wanted to take the limit in this case, what should I do? Oh yes, there was a 2 there, but it's not going to affect because the 2 is just a constant. I can take it outside of the sum. It's not going to be it's just going to be different limits, but it'll be okay. So here's what's the limit then? Well, you could use 2 to 2 over. You could use that, yes. How do I take the limit? Well, just factor out the highest order terms. So in the numerator, the highest order term is n squared. So I get 2 plus 3 divided by what? N. In the denominator, if I factor out n to the 5, I'm going to get 5 over n to the 5 plus 1, right? And I have the square root times n to the half. In the denominator now, what I'm going to do is write this as n to the 5 half times 5 over times the square root of 5 over n to the 5 plus a 1. Here I have n squared 2 plus 3 over n to the half. Okay, so now what happens? You realize that n squared, n to the half, and n to the 5 half, they all cancel out. Because n squared, n to the half is the same as n to the 5 half, right? So in the numerator I have n to the 5 half, denominator I have n to the 5 half, right? If you combine this with this, you get n to the 5 half, right? So you can cancel them out. Is everybody okay with that? You guys see that? You guys agree with me that I can cancel out these 3 terms? If you're not sure, let me know, okay? So again, n to the 2, n to the half, if you combine them, you get n to the 2 plus a half. N to the 2 plus a half is n to the 5 half, which then cancels out the n to the 5 half in the denominator. So now, if I take the limit as n goes to infinity, what do I get? Limit as n going to infinity of an over bn is equal to 2, right? Everybody agrees with that? Which is larger than 0. Okay, so by the limit comparison test, I know that either the series of an and the series of bn, they both are convergent, or both are divergent, right? Since we know that one of them is divergent, the other one should be divergent. Am I making sense? So we know, so by the limit comparison test, the series n squared plus 3n over 5 plus n to the 5 is divergent, since the series 1 over n to the half is divergent. Are we okay with what I said? So once again, I was given a series and I wanted to check whether it is convergent or divergent. What did I do? I first made a guess by simplifying the series. I made a guess that the series is divergent, and then I said, if I want to use the limit comparison test, then I have to come up with a divergent series, and then I have to take the ratio of the corresponding terms of the given series and the divergent series that I'm picking, and show that the limit is positive. If the limit is positive, then I know both series either are divergent or convergent. Since I picked a divergent one, the given one should be divergent as well. Is that making sense? Okay. Now, this series that I had, that we started with, this series, the sum of 2n squared plus 3n divided by the root of 5 plus n to the 5, okay, that's a divergent series, is exactly what we have shown. Now in your homework you'll see very similar questions, and so now you should know how to tackle all the problems in this section. All right, so everybody is doing okay with this. We are done with this section 10.4. No, not 10.4. 11.4. Okay. Well, you should start looking into the homework problems. Let me do one more example, just because I have 5 minutes left. Okay. So here's an example. Let's use. Let's say I have the given series n going from 1 to infinity of sine of 1 over n. This one is a little bit trickier. What would you guess in this case? You would guess divergent? You would guess convergent? Okay. Now, was it here or the other class? I did an example with sine of 1 over n. Was it in this class or the other class? I think you guys asked me a couple of homework questions yesterday, right? And I think in one of the homework questions, we had to find the limit of something n times sine of 1 over n, and we wrote it as sine of 1 over n divided by 1 over n. I'm pretty sure I did it, I think in this class, maybe in the other class, but okay. All right, so if you didn't do that homework problem, if you did that homework problem, you would know exactly what's going to happen here. But if you didn't do that homework problem that I am talking about in 11.1, then you might not have a good guess here. So the guess here would be this would be in fact divergent, okay? And the reason is, I'm going to compare this with with the series 1 over n going from 1 to infinity. And you might say, hey, why do you want to compare it with 1 over n again? Well, here's why. When n is big, 1 over n is very small, right? When n is big, 1 over n is very small. Now, you have to remember one fact about the sine function is that sine of theta is approximately the same as the value of the angle theta itself if theta is small. Okay, if theta is a very small angle, then sine of theta is about the same as the value of theta, the radian measure. Is that making sense? So I know that when n is big, each term of my series is about the same as 1 over n. Because when n is big, 1 over n, the angle 1 over n is small. So sine of 1 over n, so sine of 1 over n is about the same as 1 over n if n is big. Because when n is big, the angle 1 over n would be small, and I can use this fact. So that's why I'm making this guess that my series is probably divergent. Is everybody okay? So now how do I show that my series is divergent? Well, I have a series to compare with. The series that I picked, 1 over n, that's a p series with p equals to 1, and it is divergent. So let's take the limit of the corresponding limit of the ratio of corresponding terms. So take the limit n going to infinity, sine of 1 over n divided by 1 over n. So take the limit of the ratio of corresponding terms. What is that? Remember we said that this limit, maybe in the other class I said, what I'm going to do is I'm going to make a substitution here. I'm going to replace 1 over n by theta. So I'm going to take theta to be 1 over n. I am going to take theta to be 1 over n. So this would be sine of theta divided by theta, right? Now, if n goes to infinity, theta goes where? 0. Okay, if you look at the limit, theta goes to 0, sine of theta divided by theta, right? What is that? Just because it is the numerator has limit 0, denominator has limit 0, so 0 over 0 doesn't mean the limit doesn't exist. The limit is 1. Remember, this is the limit you used to find out the derivative of sine function in calculus 1. So the limit of sine theta over theta as theta goes to 0 is 1, because remember what I said, when theta is small, sine theta is about the same as theta. So the ratio would be 1. Okay? So as theta goes to 0, sine theta over theta is 1. So now I know that the limit of this limit of sine of 1 over n divided by 1 over n is 1, which is larger than 0. So by the comparison test, by the I should say the limit comparison test, by the limit comparison test, the series n going from 1 to infinity, sine 1 over n is divergent. Everybody is okay with that? Okay, you should be able to start the homework in this section. If you don't have enough time, at least do 2 problems from this section, okay? Yeah.
Were you able to locate my quiz?